how many birds usually visit your garden? Is it more or less than in your parents' garden? Often we see quite some variation in how animals distribute themselves. In some habitats, we see high densities, while in others, the number of animals is much lower. Which factors can explain this? Let's focus on two likely candidates: the availability of resources and the number of individuals already present. To better understand how these two factors can influence the distribution of animals, a theoretical model was developed: the ideal free distribution model. Models need to make assumptions, and the two most important ones for this model are that animals can ideally select habitats that maximizes their fitness, thus their survival and reproduction, and that all animals are free to move wherever they want. Additionally, three other important assumptions are made. 1. When more individuals settle in a given habitat, the fitness of each individual goes down due to increased competition. 2. Individuals are equal in their competitive ability. Thus everyone is equally like to win a conflict over resources. And animals have complete knowledge of how specific amounts of resource availability and competition will affect their fitness. Theoretical models of animal behavior can be used to generate specific predictions that can then be tested on real animals. For example, the ideal free distribution model predicts that individuals should distribute themselves according to habitat quality. So habitats of higher quality should contain more individuals. And in the end, all animals should have the same fitness, independent of where they settle. When a group of animals can choose between a high-quality habitat and a low-quality habitat, individuals will first go to the high-quality habitat, because that will lead to the higher fitness. But with each individual that joins the high-quality habitat, competition increases, and thus the fitness of each individual goes down. At some point, it goes down so much that the fitness level of individuals in the high-quality habitat with many competitors becomes equal to that of being in the low-quality habitat with fewer competitors. And thus it pays some individuals to move. After this, when the fitness expectations are equal, it does not profit any individual anymore to change habitats. This was tested on a small scale with groups of single-sex guppies. In the first trials, the guppies did not follow the model predictions. But after some time, they indeed distributed themselves relative to the available food. It seemed that the fish needed some time to assess how the food was distributed. Predictions of the ideal free distribution model are a good basis to start studying resource exploitation in animals. But of course, often the model assumptions cannot be met. Individuals rarely possess complete knowledge of their environment, as the example with the guppy just showed. Because of this incomplete knowledge, individuals are often attracted to conspecifics, as they can use the presence of others as a cue of habitat quality. This leads to more individuals on one place than the model would predict. Finally, the assumption that individuals are equal in competitive ability rarely holds. Often, stronger or more aggressive individuals can exclude each other from using the resources in a particular habitat, and thus monopolize more resources than a model would predict. To investigate how animals compete with each other, we need a different model that explores the costs and benefits of winning and losing confrontations. A good example is the hawk-dove game, based around whether to adopt an aggressive or a peaceful strategy when competing. Acting aggressive can be beneficial if you can bully peaceful rivals away from resources. But there are also risks, because you could get heavily injured if an opponent fights back. Which strategy is best often depends on the payoffs and on what other competitors are doing. Imagine that your strategy can be either to play a gentle dove or an aggressive hawk. Doves just use displays and never start physical fights, while hawks always want to fight their competitor, but thereby also risk injuring themselves. For each strategy, We then estimate the benefits and costs. For example, perhaps winning a contest has a value of plus 50 and losing has 0. The cost of injury is minus 100 and the cost of display is minus 10. Now we can calculate what happens. Let's assume that each individual has a 50% chance of winning when it meets the same strategy, and that hogs will always beat doves. Which is the best strategy to play? When dove meets hog, the dove will lose and receive 0 points. When hog meets dove, the hog will win and receive 50 points. When dove meets dove, it will win half of the time and lose half of the time, gaining 25 points on average. But it also loses 10 points for displaying each time, so on average doves gain 15 points. And finally, when hog meets hog, it will win half of the time, also gaining 25 on average. But the hog gets injured half of the time, losing 50 points on average each contest. So hogs should expect to lose 25 points per encounter with another hog. You can imagine that in a population which only consists of doves, the best strategy is to play a hog, because the average payoff of being a dove meeting a dove is plus 15, while being a hog meeting a dove is 50. However, when everyone is a hog, you do best by playing a dove. You only get 0 points, but that's still better than the minus 25 you get when playing a hog meeting another hog. And once more doves enter the population, it becomes more favorable to play a hog again. At some point, the payoffs for both strategies will be equal. And in the end, we have a stable mixture of hogs and doves in the population. A variety of strategies is indeed what we usually see in nature. Although theoretical models often start out very simplistic, they can be used to make interesting testable predictions and for gaining some insights into how certain behavioral strategies might have evolved.